Next up is problem number 3 on the worksheet. It says, consider the helix curve described by the vector function r of t, which is a cosine t, comma a sine t, comma bt, where here a and b are positive constants. And part A says to use the formula kappa equals the magnitude of the derivative or unit tangent vector with respect to time divided by the magnitude of the velocity to compute the curvature of this helix. Okay, so this is what we called formula number 1 for the curvature. And so to use it, we're going to start out by finding the velocity vector. And you find that by just differentiating the position vector component-wise. So we get negative a sine t, comma a cosine t, comma b. And then we can go ahead and compute the magnitude of the velocity, which is the square root of the sum of the squares of the components of the velocity vector. And notice here from the first two terms, we just get a squared from the Pythagorean identity, so this turns out to be the constant square root of a squared plus b squared. Okay, so then to form the unit tangent vector t, we just take the velocity and divide it by its magnitude. And so here I'm going to just take the green velocity vector, and then I'm going to put 1 over its magnitude just out in front because it's constant. Alright, so now let's go ahead and differentiate the unit tangent vector with respect to time. And so again, I can leave this constant of 1 over root a squared plus b squared out front. So I'm just going to differentiate the components of this vector right here. And that gives us negative a cosine t, comma negative a sine t, comma 0. All right, and so now I want to find the magnitude of this derivative vector. I'll leave that constant out in front. And it's going to multiply the square root of the sum of the squares of this vector. And again, by the Pythagorean identity, I just get an a squared under this root. So taking the square root and noting that a is a positive constant, this gives us a over the square root of a squared plus b squared. All right, so now we can say that the curvature of the helix is the magnitude of this derivative vector, which we just found right here. It's a over this square root of a squared plus b squared, and we want to divide by the magnitude of the velocity vector, which we computed up here, is just the square root of a squared plus b squared, and this all simplifies to a over a squared plus b squared. So our conclusion here is that the curvature kappa for this helix curve is a over a squared plus b squared, and so in fact the helix has constant curvature. Okay, so now here's a nice animation of our helix curve in blue, and this green vector you're looking at is the unit tangent vector. And so the fact that the helix has constant curvature implies that this green unit tangent vector is changing direction at a constant rate as we move along this path. All right. Great. So now let's go ahead and check out part B. It says use the formula kappa equals the magnitude of the velocity cross the acceleration divided by the magnitude of the velocity cubed to compute the curvature of the helix. Okay, this is what we call the alternative formula for curvature. And so to start out, we'll go ahead and compute our velocity vector. It's just the same as what it was in part A, and the acceleration vector, which I can find by just differentiating the velocity vector component-wise. So it's negative a cosine t, comma negative a sine t, comma 0. So now let's go ahead and compute the cross product of the velocity and the acceleration vectors. So computing this determinant gives us ab sine t, comma negative ab cosine t. And then here for the k component, we have to compute this 2 by 2 determinant. Notice through the Pythagorean identity, we're going to get a squared sine squared t plus a squared cosine squared t, which is a squared. Okay, so now I'm going to go ahead and just factor out this a from this cross product vector. So it's a times this vector here. So now the magnitude of v cross a, well, I'll leave this a out in front, and it'll multiply the square root of the sum of the squares of the components of this vector up here. And notice again, from the Pythagorean identity, we get a b squared here, and then a plus an a squared. So this turns out to be a times the square root of a squared plus b squared. All right, so now to find the curvature Well, I want to take this magnitude of v cross a, which I just found right here. It's a times the root of a squared plus b squared, and divide by the magnitude of v cubed, right? The magnitude of v, we note up here, is the root of a squared plus b squared. So if I cube it, okay, that's going to give me, well, a root a squared plus b squared cubed in the denominator, and I have a root of a squared plus b squared in the numerator. So in total, I have a root of a squared plus b squared squared in the denominator, and the squaring of the square root is just going to give me what's inside. That's a squared plus b squared. And so I arrive at that same conclusion that I did in part A. All right, very good. Well, that's a good place to stop. I'll see you in the next video.